Hello everyone, this is Swati, and today we are here for the tech talk topic, and this is a subject called flight mechanics. So you can see the topic name. So unmanned air vehicle communication purpose modeling and evolution. In this, unmanned aerial vehicles are becoming integral to various aerospace applications from radar and surveillance to deliver and communication relay UAV communication systems. Enable this aircraft to maintain real-time connectivity with ground stations, other UAVs, and satellites. The communication links between UAVs and their communication networks are critical for operational success. Path loss modeling is an essential aspect of UAV communication analysis as it qualifies to the loss of single strength as a transmission flow through the atmosphere. Accurate path loss models are crucial for ensuring reliable communication in dynamic and diverse environment encountered by UAS. As you can see in the figure, we had taken an example of quadcopter. So, so the importance of path loss modeling. The path loss modeling is a core component of communication system designed for UAV. It helps to predict how the radio signals will deviate as it travels through the air and encounters obstacles such as buildings, trees, atmospheric conditions. The degradation occurs due to several factors, including space loss, refraction, scattering, and observation. Understanding the characteristics of signal propagation is necessary to design efficient communication systems that can maintain strong links between UAV and their communication networks. Path loss models help engineers optimize power requirements and unattended design, ensuring they can efficiently transmit data over long distance. As you can see the figure, we had a UAV which are sharing their communication in between the one diameter of altitude on a floor. In next, free space path loss model. One of the most fundamental models used in UAV communication path loss modeling is the free space path loss model. This model assumes a clear line of straight LOS between the transmitter and receiver without an obstructions in the environment free space. Path loss is primarily determined by the frequency of the signal of the distance between the transmitter and receiver. If it is the official and calculated using the Searle transmission equation, while the free space modeling is useful in ideal conditions. UAV often operates environments where obstacles and atmospheric conditions introduce additional losses, making complex models necessary for accurate predictions. Factors affecting path loss in UAV communication. Several factors influences path loss in UAV communications, especially as UAV operates in dynamic and often challenges environments. These factors include the altitude of UAV, frequency of operational environmental obstacles, and atmospheric conditions. UAV flies at higher altitudes can experience reduced path loss compared to ground-based communication systems, but they may also face unique challenges such as signal fading and interference. Atmospheric phenomena like rain, snow, and humidity can also introduce additional signals. Accurately modeling these factors is essential for designing robust communication systems that maintain signal integrity in real-world conditions. As we can see in the real world condition, we have the forests, villages, and cities. In these, we can use the UAVs as the communication system. And we had an example of urban and rural parts, loss environment. The environment in which a UAV operates significantly impacts this communication link quality with urban areas, often presenting more challenges than rural settings in urban environment. Signals may experience high level of distraction, scattering, and reflection due to the presence of building power lines and other structures. This results in increased path loss, particularly in non-line of sight (NLOS) conditions. In contrast, rural environments typically offer more open space with fewer obstacles, allowing for the clearer line of sight and reduced signal degradation. Path loss models must account for this difference to provide accurate predictions of UAV communication system in various environments. Line of sight and non-line of sight conditions. Path loss modeling of UAV must also differentiate between line of sight (LOS) and non-line of sight conditions. In LOS conditions, the UAV and ground station have an unobstructed view to each other, resulting in minimal signal degradation. However, in NLOS conditions, where obstacles such as buildings and trees block and directly pass signal path, the signal experiences more significant potential. NLOS path loss models often include factors such as diffraction, reflection, and scattering, which can be complex to qualify. So UAVs, non-line of sight conditions are especially important to consider as they can occur in urban, coastal, and mountainous environments. As we can see, the signal strength due to the path loss in the trees and the households. Empirical path loss models for UAVs. Empirical path loss models based on real-world measurements and observations are often used to predict signal loss in UAV communication. These models are developed by collecting data on signal strength at various distance and environment conditions. One of the widely used empirical models in the HATA model, which provides path loss predictions for different environments, including urban, suburban, and rural areas. Other models such as COST 231 model and the Okarma-Hata model are also commonly applied. These models are particularly useful in environments where theoretical models may not accurately capture the complexity of real-world signal propagation. Modified path loss models for UAVs. In many UAV communications applications, standard empirical models may not be directly applicable, necessitating the modification of existing path loss models to account for specific UAV characteristics. For example, UAV often operate at high altitude, where signal propagation differs from the terrestrial systems. Modification may involve adjustment to the free space path loss formula to account from the altitude of UAV, which influences the signal coverage area. Additional UAVs equipped with advanced communication systems such as multiple input and multiple output, which is known as MIMO, or beamforming capabilities may experience different path loss characteristics that require specialized models for accurate predictions. So As we can see in the figure, there is a huge big area where we can use the UAVs as our main component in those areas which is having highly traffic area. So this is one type of modification in the UAVs which is used in our daily basis life structure. So the role of frequency in path loss modeling. The frequency of operations plays a significant role in path loss modeling. For UAVs, higher frequencies such as those in the millimeter wave spectrum tends to experience higher path loss due to increased signal absorption by atmospheric components like rain or fog. Conversely, low frequencies such as those in the VHF or UHF bands typically experiences lower attention but may be more susceptible to interference and multipath propagations. When modeling UAV communication systems, engineers must consider the frequency band to ensure the chosen frequency offers a balance between signal quality coverage and interference resistance. Impact of UAV altitude on path loss. The altitude of the UAV directly influences the path loss in communication systems. UAVs operate at higher altitudes generally have the wider line of sight, reducing the signal degradation caused by obstacles like buildings and trees. This results in lower path loss compared to ground-based communication systems. However, the relationship between altitude and path loss is not linear. At higher altitudes, the signal may encounter additional atmospheric effects such as increased amplification due to the atmosphere's properties. Accurate path loss models for UAV must incorporate altitude as a variable to assess how it impacts signal propagation in various operational conditions. As we can see, the communication between the UAVs and the ground control having both the connections are having perfectly all right. In UAV communication networks, in swarm operations where multiple UAVs communicate with each other to complete a mission present unique challenges for path loss modeling. In swarm, UAVs operate in close proximity and their communication links are influenced by both the direct path loss between UAVs and the interference caused by other UAVs in the network. Path loss models for swarm operations need to account for dynamic network topologies, various distances, and interference levels. Additionally, the relative motion of UAVs can introduce shifts and time-varying path loss conditions that need to be captured to ensure reliable communication in the swarm environment. Next, shadowing and padding effects. Shadowing and padding are important phenomena to consider in path loss modeling for UAV communication system. Shadowing occurs when obstacles partially or completely block the signal, leading to sudden changes in signal strength. Padding refers to the rapid fluctuations in the signal strength caused by the interference, multipath propagation, or movement of the UAV. Both effects can severely degrade the quantity of communication links. Path loss model needs to account for this effect by incorporating statistical models such as long-normal shadowing model to predict the variations in signal strength due to environmental changes and wave motion. Simulation-based path loss evaluation. Simulation tools plays a vital role in evaluating and refining path loss models such Wavy communication system. Using software like MATLAB or specialized wireless simulation tools, engineers can simulate UAV flight patterns, environment conditions, and signal propagation to evaluate the performance of communication links. These simulations allow for the test, testing of different path loss models in various scenarios, including urban, rural, and mountain. Environment simulations based evaluation provides visible insight into the effectiveness of path loss models, helping engineering optimize based communication system parameters such as power levels, antenna placement, and frequency selection. As we can see in the diagram, we had a base and the UAV around the city, it is having a strong power level and frequency selections of with the system of parameters. Path loss in dynamic and variable environment. UAVs often operate in dynamic and variable environment, making path loss modeling particularly challenging. For example, in a military scenario, UAVs may fly through areas with rapid changing weather conditions and obstacles, all of which affect signal strength. In such situations, traditional path loss models may not fully capture the impact of these dynamic changes. Advanced models the incorporate real-time data and environmental conditions such as wind speed, humidity, and temperature can improve the accuracy of path loss predictions. These dynamic models are essential for designing a resilient communication system capable of adapting to rapid changing conditions. As we can see, the one drone is communicating with many drones with many operators. So next, channel estimation and path loss prediction. Accurate channel estimation is crucial for improving path loss predictions in UAV communication systems. Channel estimation involves measuring the challenges characteristics including noise and interference to estimate the path loss more precisely in UAVs. The channel is often time varying due to their motion. The environmental changes advanced techniques such as adaptive filtering, machine learning, and Kalman filtering can be applied to continuously update the path loss predictions based on real time. This enables UAVs to maintain reliable communication links even in challenging conditions where traditionally static models may not be effective. Path loss modeling for communication relay. UAVs are increasingly being used as communication relays, especially in remote or inaccessible areas. In this scenario, UAV acts as intermediaries, forwarding signals between ground stations or other UAVs. Path loss modeling for communication relay is crucial for ensuring that their relayed signals remain strong enough for successful transmission models. Must account of additional distance between the relay UAV and both the source of destination nodes. The complexity of relay communication system requires more sophisticated path loss models and captures both direct and indirect signal paths, ensuring efficient operations in relay-based network. As we can see, there is a small part of an UAV, which is the main requirement of in the UAV, which is the receiver, which receives the signal from the transmitter and passes to the board. Real-time path loss measurement and calibration. Calibration is one of the main parts of the UAV. Let's see. Real-time path loss measurements and calibration are essential for maintaining the accuracy of UAV communication systems in dynamic environments. By conducting field measurements of signal strength at various distance and environmental conditions, engineers can validate and refine their path loss models. UAVs can equipped with sensors and to measure path loss in real time, providing valuable data and to adjust the model parameters dynamically. This measurement helps to ensure that the communication system operates efficiently and that single strength remains accurate for reliable data transmission even when environmental conditions fluctuate. Long-term path loss consideration. Long-term path loss considerations are important when evaluating the performance of UAV communication systems over extended period. UAVs used for tasks such as surveillance, environmental monitoring, or communication relay may need to operate for hours or even days at time. Over long duration path loss can vary due to environmental changes such as seasonal shifts or construction of new buildings. Long-term path loss modeling must account for those factors to ensure that the communication system remains reliable throughout the UAV. Operationally, lifespan, this requires continuous monitoring and adaptation of the communication system to changing environmental conditions. At last, to conclusion, path loss modeling and evaluation are fundamental to ensuring the reliability and efficiency of UAV communication systems. In aerospace application, accurate path loss models help engineers signal degradation, optimize power levels, and improve overall system design. By accounting by accounting for environmental factors, UAV altitude, and other dynamic variables, path loss model enable the development of robust communication systems that maintain connectivity under a wide range of conditions. As UAV continues to evolve and find the new applicants, advantage and advertisement in the path loss modeling will be crucial for ensuring their effective and reliable operation in the aerospace industry. Thank you.